Okay, now we're going to look at the last section of chapter 3 from the book, which is using determinants in a few different ways. So, first thing is called Cramer's rule, and this is in its theorem 7 in the book. It's called Cramer's rule. It has to do with solving systems of linear equations. So up until now, we saw that how you solve a system of linear equations is you take your matrix, you augment it, you row reduce it, then from there you can figure out what your solutions are. Cramer's rule gives us another way to find solutions to systems of linear equations. So when you have a system of linear equations, ax equals b, where A is a square matrix, you can solve for any of the elements in X by finding the determinant of this AIB. Now, what is AIB? This is where you take your original matrix A, replace the ith column in it with your coefficients B. Take the determinant of that, divide it by the determinant of your original matrix A, and you get the solution to the ith element of X. So here's an example of it. As an example, using some constants in there as well. The book actually has a few other examples too to follow through. So find the values of S for which this system has a solution. So first off, what is this? If we rewrite this as AX equals B, what do we get? Well, our matrix is 8 minus S, 4, 2, and 2 minus S, times our X, X1, X2, is equal to B, which is 5, 3. So I've rewritten it in matrix form. Now, from an earlier lesson, you may recognize this matrix A. It was one that we had earlier. We figured out that the determinant of A is equal to S minus 6 times S minus 4. If you don't remember that, figure it out quickly. That gives us our determinant. So now we're being asked where it has a solution. What is the solution? So there is a solution when S is not equal to 6 and S is not equal to 4. But what is that solution? So there's our original equation. What do we do now? Well, we want to figure out what x1 and x2 are in that matrix. So to get x1, we need to use the matrix A1B. So what does that mean? We take our matrix A and we replace the first column by B. So A1B is equal to 5, 3, and then the second column of what we had originally, negative 2 and 2 minus S. And now we're going to get the determinant of that. So the determinant of A1B is equal to 5 times 2 minus S minus negative 2 times 3, which when you multiply it all out gives you 10 minus 5S plus 6, or negative 5S plus 16. So there's that determinant. Now that gives us a value for x1, which is that divided by the determinant of A, negative 5S plus 16 over the determinant of A was S minus 6, S minus 4. So whatever you give me for S, I now have the value of x1 using Cramer's rule. What about the second one? A2b, well, you take A and you replace the second column of A with my values for B and figure out the determinant of that. So the determinant of A2b is 8 minus S times 3 minus 5 times 4. Figure this all out, we get 24 minus 3S minus 20, which gives negative 3S plus 4. So x2 is equal to negative 3S plus 4 over S minus 6, S minus 4. Now Cramer's rule has given me my solution. So that means that my matrix x1, x2 is equal to negative 5s plus 16 over s minus 6, s minus 4. And my second value is negative 3s plus 4 over s minus 6 times s minus 4. So Cramer's rule uses determinants, and determinants can give you the solution to your system of linear equation when you apply them this way. Theorem 8. This is a way of finding the inverse of a matrix using a determinant. Now we saw that when you have a 2 by 2 matrix, we saw that the inverse of a 2 by 2 matrix, where A is equal to ABCD, is equal to 1 over AD minus BC times AD negative B negative C, like that. So this can be generalized to larger matrices. Theorem 8 says that the inverse of a matrix is 1 over the determinant minus the adjunct matrix of A. What is the adjunct matrix of A? The adjunct matrix of A is taking all of those cofactors that we've been using for figuring out determinants, putting them in a matrix, and transposing them. So adjunct matrix is the transpose of the matrix of cofactors. And you can see that's exactly what we have here. What is the 1, 1 cofactor of A, of our matrix A up above? The 1, 1 cofactor is when you eliminate the first row in the first column. What are you left with? D. And I have that backwards. Continue through all of them, and you're going to get exactly what we've already seen for the inverse of a matrix, of a 2 by 2 matrix. And my apologies here, but I wrote this down backwards. This should have been negative B and negative C, like that. But you can see where that is that is using exactly this theorem, just on a 2 by 2 matrix, which we've already seen. This theorem says how we generalize it to larger matrices. Okay, so now we're going to look at a geometric interpretation of determinants. The determinant actually gives us the area of a surface on a two-dimensional plane. So, what do I mean by that? If you have any two non-parallel vectors in R2, you can build a parallelogram out of them. So V1, V2, and U1, 0. Let's assume it's kind of lying on its side here, so that one of the sides is flat. What is the area of that parallelogram? Well, if you remember from your geometry, your basic geometry, the area of a parallelogram is the width times the height, or the base times the height. So what's the base times the height? Well, the base is u0. The height is v2. So the area of that parallelogram is u1 times v2. What's the determinant of those two vectors? The determinant of the vectors were u and then v, you figure that out, it's u1 v2, which is exactly the area of the parallelogram. What if you put the vectors in the opposite direction? So just flip around the order of the vectors in my matrix, I get negative the area of the parallelogram. So what you have is the area of the parallelogram is always going to be the absolute value of the determinant of the matrix formed by putting the vectors in the columns of the matrix. That same idea applies to 3 dimensions. If we have any three-dimensional vectors, they form what is called a parallelepiped. So they form this object where the corresponding edges are parallel. The determinant of the matrix formed by sticking those 3 vectors together is the volume of that parallelepiped. And theorem 9 sums that up. So the determinant actually gives us a physical measure in the real world. When you're forming these parallelograms or 3-dimensional parallelepipeds or even multi-dimensional parallel objects, determinants give you the measure of their area, their volume, or their multi-dimensional volume. Finally, when we look at transformations, we spent some time with linear transformations, where we kind of take a vector and convert it to another vector. Well, you can think of transformations changing surfaces as well. So for instance, if we have on our plane, we have some kind of a surface, say a circle, we can think of transforming it through a linear transformation T, where you take every point in there and plot it out after the transformation. You will get some kind of shape over here. What's the relation between the areas? So we have an area of our original shape. What's the area of our transformed shape? Well, it's the area of what we start with times the determinant of the matrix related to that transformation. Matrices, again, are related to areas. If we have an area and we transform it with a linear transformation, the area of that new object is what we started with times the determinant of the matrix that was used to transform it. When you're dealing in 3 dimensions, it's the same thing. When you transform something in 3 dimensions with a linear transformation, the area you start with times the determinant gives you the area you end with. So once again, determinants have this connection to a physical quantity of area or volume. So this chapter was looking at a few uses of determinants. You'll notice when we talked about transformations and determinants and so forth, linear transformations, there's lots of applications of this to computer graphics. So in the background on a computer, when there's computer graphics transformations going on, for instance, if you use some of the more popular programs, it actually uses matrices, matrix multiplications, determinants to figure things out. What happens to a surface, to a shape after a transformation? So there are real world applications for these ideas of linear transformations and the determinants of linear transformations and the impact they have on surfaces.